Welcome back. In this lecture, we're going to discuss conditional statements in more depth, and this material is going to be pulled from chapter 3 of our text. So conditional statements are of the form P right arrow Q, and there are at least 6 different ways that we can pronounce that symbol. The first way that I taught you was if P, then Q. But another way to think of that is Q if P, right? So Q if P just means that you can read that as, tacitly saying Q follows if given P. Another useful way to express it is P only if Q. P implies Q. P is sufficient for Q, and Q is necessary for P. So these last two, the sufficient clause, this just means that as soon as P is obtained, it's going to follow that Q will come up. And Q is necessary for P. This means that there is no instance where you would have P obtain but without Q, right? So it's necessary in that sense. Okay, so I previously said that the conditional statements are quite odd. They result in some very weird conclusions, and so here we're going to go through some examples. So the statement if Paris is in France, then 2 plus 2 equals 4. So if Paris is in France, then 2 plus 2 equals 4. And then if Paris is in France, then 2 plus 2 equals 5. How about if Paris is in England, then 2 plus 2 equals 4. And if Paris is in England, then 2 plus 2 equals 5. Okay, so I'm going to make 2 comments on this. One is just the truth values of these statements, and then a brief comment, some sort of brief comment about causation and correlation. Okay, so the first statement is very obviously true. Paris is in France, 2 plus 2 does equal 4, so it's very difficult to see how this could possibly be false, so it's got to be true. The second one is definitely false because, in fact, Paris is in France, and 2 plus 2 does not equal 5. So for this statement to be true, because Paris is in France, right, if this statement were true, so if the statement, if Paris is in France, then 2 plus 2 equals 5, if it were true, then from the fact that Paris is in France, we would be able to conclude that 2 plus 2 equals 5. However, 2 plus 2 does not equal 5, therefore the statement is false. The third one is true because, in fact, Paris is not in England. So this is true. But also, the fact that the consequent is also true would make the whole thing true regardless. So that's something that these two have in common, right? The consequent is 2 plus 2 equals 4, and so we see that it doesn't really matter if the antecedent is true or false. It's going to be true either way. So this one's true for 2 reasons. Namely, the antecedent being false and the consequent being true. Finally, this last proposition is true simply because the antecedent is false. Okay, so that does it for just the truth values of these statements. I said we would do that. And now I would like to just make a general remark. The odd thing about the implication symbol, material implication, implies symbol, conditional statements in general, is that any true statement implies any other true statement. But typically when we use implication language, we think of there being some sort of correlation or some sort of cause. Like we say, if you heat this water, then it will boil. But in fact, it could be something two very unrelated things. Like if you blow hot air in a balloon, the water in the sea is blue, right? The two have nothing to do with one another, and yet the statement is true, right? Okay, so enough about that. Let's move on. So now we're going to get into biconditionals. So a biconditional is a statement of the form P double arrow Q, and we pronounce this P if and only if Q. And it's called a biconditional because the conditional arrow goes both ways. And when you just had P implies Q, this was still a conditional statement. Conditional in the sense that if the statement is true, if the statement P implies Q is true, then provided P is true, that condition being satisfied makes Q true as well. So one way to think of, perhaps the best way to think of material implication is that it is truth preserving. So provided it is true, then given a true statement, we can conclude another true statement, namely Q. So that's the best way to think about it. So what should this symbol be? Well, if you recall from a moment ago, I said that one way to pronounce P implies Q is P only if Q. Another way to make sense of this is Q if P, right? So combining these statements, we can easily see, I mean, just breaking this word down, if we break it down, it is if and only if P, and perhaps, so another way to read this is P, that should be a Q, sorry. Perhaps one way to read this is P only if Q and P if Q, right? So I just took this last sentence and sort of just rewrote it. Okay, so what does this mean? Well, P only if Q, just by what I wrote over here, what we discussed earlier, this would just be P implies Q, right? And now I've got this and symbol, and so I can, not symbol, I have the word and. Okay, and then earlier I said that, well, I've got it written right here, right? So Q if P, that's this. So if we swap these to make it P if Q, then if we swap those, we'd have to swap the order of those. And so we can see that it would have to be this, right? And so this basically shows it's all consistent. So in summary, the point I'm trying to make is that this double arrow is just the arrow facing both ways, right? So you get both things, right? We also like to pronounce this as P is necessary and sufficient for Q, and a few other ways. Okay, so what are some facts about this? Well, what it means is that the truth values are going to be the same for P and Q, provided P if and only if Q is true, right? So let's see that. So we're going to use a truth table, and your book actually defines P if and only if Q by a simpler truth table, just having these first two columns and then the final column. But I think that's a little misleading, because it seems to me that just by using the words if and only if, right, if we just think about how those words work, then by what I had just done before I erased the board, you can basically see that you need to know the values of these to determine that, right? Because this is just this and that. Okay, so there are two variables, so there should be 4 rows. And let's go through here and assign some values. So true, 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 false, false, true, and false, false. Good. Okay, now I'm going to make the intermediates red. Okay, so this is true, this is false, right? Because the antecedent is true and the consequent is false. These two are true because the antecedent is false for both of them. Okay, so over here, let's be careful. So this is our first column, and this is our second column for this case, right? So again, this is going to be true. This one and this one are going to be true because the antecedent is false. So I'm going to go ahead and write that in right now. And if the antecedent is true and the consequent is false, the whole thing is false. Okay, so this, right, this is going to be true just in case both of them are true, right? Both of these, right? Because remember, this is just short by the discussion I gave a second ago. It's just short for saying this, right? After all, it's P if and only if Q, which is the same thing as saying if P then Q, and Q if P. Okay, so clearly this is true because those are true. At least one of these is false, so the whole thing is false. This is false, and this is true because both of those are true. Okay, so in summary, we see that P if and only if Q is true just in case, right? Just in case is just another way to say if and only if, but I don't want to confuse you. Yeah, so P if and only if Q is true precisely when both of them have the same truth value, right? Right here and right here. Okay, so if we go back to our Paris is in France example, right, then the statement Paris is in France if and only if 2 plus 2 equals 4, that is true because Paris is in France, 2 plus 2 does equal 4. Paris is in France if and only if 2 plus 2 equals 5, that is false, right, because the first half of the statement is true, but the second half is false. Paris is in England if and only if 2 plus 2 equals 4. That is also false, right? Because Paris is not in England, however, 2 plus 2 does equal 4. Finally, Paris is in England if and only if 2 plus 2 equals 5. Absolutely a true statement, because neither of them are true. Okay, so I'm going to end this video by making a brief comment on converse, inverse, and contrapositive. Okay, so there's a table, I believe it was made by Aristotle, or at least it's often attributed to him. It has 4 parts, and it's basically summarizing what we're about to go through. Okay, so P and Q, these are the atoms. And as usual, there can be 4 rows, right? Okay, so okay, so this could be true and true and true and false and false and true and false and false. Okay, so this first one, this is just your standard conditional. We've already discussed it at length. Then you have your converse, and I'll make a comment about that in a second. Your inverse and your contrapositive. Okay, so P implies Q. This is, again, it's only going to be false when the first part is false and the second part is, when the first part is true and the second part is false. Now, the contrapositive is actually logically equivalent to P implies Q. And if you don't see why that is the case, go ahead and just stare at it for a second. Okay, so you have Q, not Q implies P, right? And what is that equal to? Well, it's equal to, we can put a little parentheses around this maybe to help. So if we get rid of that arrow, we can say it's not Q or P, but this is just equivalent to Q or P. And I seem to have forgotten my little tilde here in front of P, right? Okay, so this is equivalent to not P or Q, but that's just P implies Q. Okay, so that's one way to show that they have to be equal. The inverse, this one's a little tricky, so it's actually true, true, false, true. And the converse is equivalent to the inverse. True, true, false, true. So a lot of people, and the converse and inverse are equivalent in exactly the same way that the original conditional and the contrapositive are equivalent. So to be clear, there isn't anything special about the letters P and Q. We're just saying that if you start off with P implies Q, then the statement Q implies P is a converse. So for example, if I were to say all men are mortal, right? What would the converse be? How about all mortals are men, right? That's what the converse would be. So to see why these are not equivalent in general, you can come up with some simple examples. And again, the reason they're not logically equivalent is because the columns are not the same. But and you can check this. It's very similar to this calculation I did down here. But let's just think about it heuristically for a moment. Okay, so all cups of coffee are, well, let's say all yeah, all coffee is a drink, but not all drinks are coffee, right? And so it is true that all coffee is a drink. You know, maybe some of you are going to think, well, what about the coffee beans? That's not what I'm talking about. I mean, the liquid you drink, it is a drink, right? But there are a lot of drinks that are not coffee. For example, tea, milk, water, beer, etc., right? Tons of drinks. So one thing a lot of people do quite often is they make the logical fallacy. It's called, oh gosh, I can't think of it right now, but I will discuss it perhaps in the next video. Oh yes, affirming the consequence. That's it. So affirming the consequence. This is when you you know that this is true. P implies Q is true, and so someone says, "Oh hey, there's a Q, therefore there has to be a P," right? So lots of examples we can think of if you take your time. Okay, so I think that's going to be it. I will assign you some questions on this material, but that's pretty much it for semantics. In the next video, we're going to start syntax.